If your data isn't nice and round, KMeans lies. DBSCAN finds real clusters and flags outliers automatically. This is the workflow you'll know how to run when we're done, which suggests a neighborhood size from points and then groups dense regions while flagging outliers automatically. I'm Professor Pi, teaching AI foundations with simple Python. Real data rarely makes clean circles. Geospatial hotspots, customer browsing paths, or biological shapes often curve and bend. In those cases, a centroid-based method like KMeans will slice through a shape and call it multiple clusters. DBSCAN solves a different problem. It groups points that live in dense neighborhoods and treats sparse points as noise. That behavior is useful when clusters are elongated, crescent-shaped, or when you want automatic outlier detection. We will demonstrate this on a classic non-spherical example, so you get a feel for how to pick a neighborhood size and how DBSCAN behaves. Intuitively, DBSCAN asks two questions for each point. How many neighbors live close by? And is that count high enough to call the point core? If it is, DBSCAN links nearby core points into a cluster. If not, the point can become an outlier or be assigned later as a border point. Strengths are shape awareness and outlier flags. Weaknesses are sensitivity to the neighborhood radius and to the local density scale. We will build a small pipeline so you can repeat this pattern. First, we prepare a 2-moons example that breaks KMeans. Then we fit KMeans as a baseline and compute a silhouette score to quantify fit. Next, we estimate a practical neighborhood radius using nearest neighbor distances. Then we run DBSCAN and finally compare silhouette scores only on in-cluster points. That keeps the code focused and the steps reproducible. Now, we'll generate and prepare a toy non-spherical dataset. This snippet creates a non-spherical 2-moons dataset and scales it so density-based clustering like DBSCAN works consistently. The function makeMoons builds two interleaving crescents with controlled noise, which is a classic shape where KMeans struggles. StandardScaler centers the features and gives them unit variance, ensuring distance-based methods use comparable axes. The variable C stores the feature-wise mean, and spread computes the average distance from points to that center as a simple, scale-stable size indicator. The array X holds the prepared coordinates that later steps will cluster. The printed spread conveys how dispersed the standardized dataset is, confirming it is ready for distance-based analysis. Next, we'll fit a spherical baseline to see how it handles curved shapes. This example fits a simple KMeans baseline and quantifies its quality on the moons. The KMeans object requests 2 clusters and uses a fixed random state for reproducibility. Then fitPredict assigns each point. The function silhouette score evaluates separation and cohesion, where higher is better, and values near 0 indicate overlapping or elongated shapes being poorly captured. The variable KMLabels stores the assignments that KMeans imposes, which tend to slice crescents incorrectly because it prefers spherical partitions. If n clusters were set incorrectly, the score would often drop further. The printed sil KMeans score provides a reference point to beat with DBSCAN. Now, we'll compute a data-driven hint for the DBSCAN radius using neighbor distances. This code estimates a good DBSCAN neighborhood radius by analyzing k-nearest-neighbor distances. The NearestNeighbors model, with n neighbors set to 4, measures local density. Then neighbors returns each point's distances to its nearest neighbors. The last column, dists-dike -1, captures each point's kth distance, which grows sharply near cluster borders and outliers. Sorting these values and taking the 90th percentile forms EPS, a practical heuristic that includes most in-cluster neighbors while excluding sparse regions. Increasing the percentile raises EPS, merging clusters and reducing outliers. Decreasing it tightens clusters, but may fragment them. The printed EPS hint suggests a data-driven starting point for DBSCAN. Next, we'll run DBSCAN with that radius and inspect labels and noise. This snippet runs DBSCAN using the EPS hint and a small min samples to uncover arbitrary-shaped clusters and outliers. The DBSCAN object defines the neighborhood radius and the minimum points to form dense regions. And fit-predict assigns labels, marking noise as -1. The variable db_labels holds the results, where unique non-negative labels represent discovered clusters. We count outliers by tallying the -1 label, and compute the number of clusters by counting distinct non-negative labels. Increasing EPS or decreasing min samples grows clusters, and usually reduces noise. The opposite tightens clusters, and increases detected outliers. The printed clusters and noise confirm that DBSCAN found shapes and flagged anomalies. Finally, we'll compare the clustering quality while ignoring the noise points DBSCAN flag. This snippet measures DBSCAN's clustering quality on the in-cluster points and compares it to the KMeans baseline. The Boolean mask M filters out noise labeled -1, keeping only points considered part of clusters. The function silhouette score then evaluates cohesion and separation for DBSCAN structure on these points. The variable gain computes the improvement over SIL KMeans from earlier, summarizing how much better the shape-aware model fits the data. If EPS were increased too much, SIL DBSCAN would often drop as clusters merge. Too small, and fragmentation also reduces the score. The printed SIL, DBSCAN, and gain show DBSCAN's practical advantage on non-spherical shapes. This toy pattern maps directly to many real projects. Replace the moons with GPS traces to find irregular hotspots. Replace coordinates with embedding vectors to cluster semantically similar short texts where clusters are not globular. The neighbor distance heuristic scales to larger sets by sampling distances or using approximate nearest neighbors. The same sequence: prepare, baseline, estimate radius, run DBSCAN, evaluate on in-cluster points, gives quick insight before committing to production. Recap in 3 points. What it is: a density-based clustering method that groups dense regions and marks sparse points as noise. When to use it: when clusters are irregularly shaped, or you need built-in outlier detection. One caveat: results hinge on choosing the neighborhood radius and density threshold carefully. Next step: tune the EPS and min samples grid using the neighbor distance percentiles and silhouette on in-cluster points to find a stable operating point before scaling up. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.